My name is Kayvon. Most students end up calling me Professor Kayvon because I'm still young enough not to be called by my last name. So most people end up calling me Professor Kayvon. Professor Bryant is also a co-instructor this year. So they've called in the big guns and the A-team to help teach the class this year. So we have some very distinguished, or at least one distinguished professor, and we have some really good TAs as well. I don't know how many of my TAs are here. Greg's here. Okay, well we have some great TAs. They're not all here, but okay. So so that's the high. So that's me. There's Professor Bryant, and you have 5 TAs, and we might be adding one more this year. So I like to always start this class by asking the philosophical question of why are you here? Because there's 190 people on the wait list. There's a lot of other people that would love to be here. Why are you taking this class? I'm always interested to hear what everybody says. Yeah.
I was interviewing with a company, and an alum from the school said you should totally take parallel.
That's a useful reason to take a class. Anything else? Anybody doing work like independent studies or research and things that they think this class will help them with? Cool. I got a couple people. Anybody else? Why are you here?
Why not?
Systems elective? Why not be here? Well, I like to be constructive about things, so yeah. Okay, so yeah, nobody's got into anything technical. So seriously, why are you taking this class? What is interesting about this class that you feel like it's worth learning? Yeah.
I want to make things go faster.
You want to make things go faster? Okay, that's a good reason.
This single monolithic view into computing I think it's outdated in this world of making CPUs run faster and faster is not as the same as what you're trying to do right now, which is make it more parallel. And to take advantage of it and to be prepared to.
Now, in a sense, I would say that they're going more parallel because they are trying to make things faster.
Yeah.
So they're still trying to approach the same goal of running more efficient or running faster, but they're doing it with different means, and that's going to all have a big implication on all of you as software programmers or hardware architects, and that might be a reason why a lot of us are here. So one of the reasons why we're here, the reason why I'm here, the reason why I love to teach you guys about this stuff is that we're here to build efficient systems, and sometimes efficient means fast. Sometimes efficient might mean something very different, like energy efficiency or resource efficiency. So we're here to build very, very efficient systems. And since this is a class on parallel computing, we are going to get that efficiency in many cases in the class by using a bunch of different many processing elements. So we're going to build machines and use machines that use a bunch of processing elements because we want to run things faster or more efficiently. So there's no reason for me to waste your time, so how about we jump right in and write our first parallel program of the year. So I need a volunteer to help me write the first program of the year. In fact, this one's not going to be parallel. So I need a volunteer. Oh, by the way, this class is filmed for your convenience, and I do need to let everybody know that this class is filmed, and if for some reason you do not want your head or somehow to inadvertently be captured on video, there might be many other classes for you to take at CMU. So anyways, with that in note, could we have a volunteer, please? Let me go to the back of the room, because I know you guys are already sitting in the front of the room. You're going to participate in everything. I need a volunteer. Somebody. And the prerequisite, come on up. And the prerequisite is you need to be able to add single-digit numbers. That eliminates the front row. Okay, so what I'd like you to do, what I'm handing you here is just a list of numbers. Okay, there's 16 numbers here, and nobody's judging you. I make mistakes when I'm adding these up. But what I want you to do is I want you to add up all these numbers. Okay? Now don't take a look at them yet. The first one's 5. But what I'm going to do is I'm going to put you on a clock. So I want to time how fast you add up all these numbers. Okay, so it makes sense? You may want to, just so we don't we don't mess up our experiment, you may want to like lick your fingers or something, so there's like sometimes they get stuck together. So, okay. Sorry, what is your name?
I'm Robert.
Robert, nice to meet you. Okay, thank you, Robert, for being my volunteer. So you ready? Set, go. That is correct, I believe. Yes. Nice job, Robert. So, Robert, you got that done in just under 40 seconds. So, very good. So, thank you very much. I know there's an Apple Watch up here, but that's actually, sorry, that's for something else. But thank you very much for volunteering. Okay, so thank you, Robert. Okay. So now let's say, so our program was add up all these numbers. And so let's say we wanted to make it go a little faster. Let's say we weren't happy with adding up this list of 16 numbers in 40 seconds. So what's one way we can make it faster? One way we can make it faster is we could tell Robert to just go practice. He needs to add up these numbers faster. You know, like I bet if Robert sat up here all afternoon, adding up integers, he'd kind of work out some heuristics, and I bet he could get that 40 seconds down to 25 or 30 seconds if he wasn't standing in front of 150 people and so on. Okay, so what else could we do to make this faster? I want to know the sum of, conveniently, another 16 numbers which I've printed out, a different set of 16 numbers. How can we make it faster? Find someone else to help you. So why don't you grab a friend? No. So here, why don't you come up and help me? Yes. Okay, so here's your list of numbers. And I'm giving you half of them, so hold on, don't start counting. And I need somebody in the back of the room. I need somebody in the back of the room to participate in this first parallel program that we were writing. It's just adding numbers. Come on, somebody over here can help me out. Please? Please? All right, okay. What is your name? Clayton. Clayton, nice to meet you. Here are your numbers, but I want you to actually, you can actually count these from your seat. Yep. You can add them up from your seat. Okay, so we have Clayton in the back of the room. Sorry, what's your name? Rizal. Sorry? Rizal? Rizal, nice to meet you as well. Okay, so I want you two to add up these numbers. And I want to know the sum, and the answer is going to be different, but I'm going to give you one rule. One rule is that you cannot talk to each other. You can only exchange information by writing on this piece of paper right here with this pen. Okay? So I'm about to start the clock, and I want to know the sum of you two's numbers. But hold on, can't start. All right, ready? Because remember, one person counted this in 40 seconds. Okay, ready? Go. $117, that is also correct. Very nice job. Thank you, guys. Okay, so we went from 40 seconds from one person to two people getting the job done in 25 seconds. So how much faster are we? Are we twice as fast? Not quite twice as fast. So I used two people to do the job of one person, but I'm not twice as fast. And so, what happened?
There was a bit of lag time because he had to come all the way to the front to see the first number.
Clayton had to start at the back of the room, and walk all the way to the front of the room. And one thing that you might not have noticed is they actually didn't have to add up very much in their head, so I think that their actual math got a lot faster than adding up 16 numbers by yourself. So the overhead of walking, like they were actually done, I think both of them in 15 seconds almost. And the overhead of communicating that information from the back of the room to the front of the room was actually about 10 seconds of that time. So how could we have made that program faster? Yep. I could have put them right next to each other and eliminated that time. That's true. I could have done something else. I could have changed the rules, right? I could have allowed them to shout or something like that, right? So in both of those cases, that's an example of me eliminating the overhead in this computation, which actually ended up being almost half the time. So if you were to say, what speed up did we get from 2 people versus 1 person? What speed up did we get in this program? It wasn't 2x, it was a little bit less than 2x, right? So this measure of speed up is a very important measure that we're going to think about all the time in this class, where the speed up of a program using 2 processors in parallel is the amount of time it takes using 1 processor divided by the amount of time it takes using P processors, or 2 processors in this case. And so if we could eliminate all of this overhead, whether that be Clayton walking from the back of the room all the way up here, or whatever that overhead is, that is going to be really, really important to getting sort of to this perfect speed up, which in this case would have been 2, right? And if I have P processors, what would the perfect speed up be in an ideal world if you write an amazing parallel program? It's P, right? Good. Okay. So your class observations from demo 1 is that communication was limiting the maximum amount of speed up achieved, and that minimizing the cost of communication is probably the key thing for us to get to that perfect speed up. I didn't do a demo where I moved you 2 both together, but had I wanted to print out some more numbers, I would have had that demo ready to go. Okay. So let's keep scaling up, because that's what we do in this class. So now I need 4 volunteers. I'd like all 4 of those volunteers to come down here, because we're going to eliminate this communication overhead from the system. Okay, so I need 4 volunteers. How about from this side of the classroom? Well, no. Yeah, come on. Come on down. Volunteers? Volunteers? I need 4. Come on down. Thank you. Yeah, come on. And then one more. From the back. From the back. Greg, you can't volunteer. I thought I saw Greg's hand. Okay, we need one more person because right now my code will not compile with only 3 humans. Okay. So I'm going to eliminate some things here. Okay. All right, thank you. So what is your name?
Rachel.
Rachel, nice to meet you.
Vivek.
Vivek, nice to meet you.
Billy.
Billy?
Evan.
Evan, nice to meet you. Okay, so here's what we're going to do. We're going to do the same program again, but there's 4 of you working together, and it's going to be by the same rules, no talking. You just write your partial sums here, something like that. And I'm going to go ahead and give everybody a pile. So, okay. And hold on, you can't look at or open your pile yet, or you can open it, but don't look at it yet. And we're going to do the same thing. So if this was a perfect speed up, what should the time be? 10 seconds, right? 40 divided by 4. So let's see how this is going to go. All right, ready, everybody? Go. $118 is correct. 17.88 seconds. Not much faster than those 2 guys. So what did people notice about this demo? It's a little subtle than it is in most other years, actually. But yeah, what did you notice about the demo? What was the shared resource? The pen, yes, okay. Yeah? They didn't all have the same amount of work. So what did you notice? So who got done first? Rachel got done first because she's clearly smarter than everybody else. And Billy, I believe, was the long pole. And clearly, he doesn't know how to add any numbers. So could you tell everybody how many numbers everybody got? I think I gave you 1, 2, 4, and you had 8. Okay. So we had a situation where I had 6, there's no more work than what anybody else was doing, but Billy ended up with most of it. So while everybody else was done, you were like hoping you could help out probably. But Billy was like just sitting there doing his thing. And so we had this unequal distribution of work to all the people. And how did that impact our ability to get this perfect speed up? They're not doing anything. They're not helping out. So if they're not doing anything, how could I possibly get perfect speed up? Did anybody notice something happened at the very end?
So Billy had to, in the end, sum up all the other results as well.
So Billy ended up doing some work. Well, first of all, we had already serialized the whole computation because only Billy was working before that. And then also we had this part that had to be serialized at the very end, which was adding up the 4 partial sums, right? And so that caused some time because those were kind of bigger numbers to add too, so it took a little bit longer. Okay, so here's what I'm going to do is you, unlike the other folks here, have another shot at this. So I made you 4 other piles, and I'm going to just randomize them here. Now, I'm going to give you guys 1 minute to talk over a strategy. Now, so now you can design your algorithm however you wish. The rules are still the same. No talking once the timer starts. You can design the algorithm however you wish. Question?
Can we like get a sense of as to how many numbers we have prior to starting?
No, I'd like you to design an algorithm that will work for any distribution that I give you. Yeah.
Can we
So
change the distribution?
you can do whatever you want once the timer starts. You can just not talk to each other. Okay, so I'll give you 60 seconds to plan this out a little bit. You can't look at the numbers. That is an optimization called pre-computation for everybody in the audience. Okay, so
So can we talk during the first minute? We can't. Yes.
you cannot talk, but you can, yeah, you can just, you're coding right now. Yeah.
We could also do like a load balancing thing where like you just have blocks just share really quickly.
So we're gonna make like one big pile of four. And each of us just okay. And then
So just put it like.
Okay,
Okay, and then like you guys add your numbers together.
this is called over-engineering. Okay, so you ready? Okay, so tell me, ready, set, go.
still 118.
Stop. So that was 18.2 seconds. So, what did we learn from this demo? This is actually something that will happen to you in this class. What did you observe about this demo? I was chuckling to myself when you were coming up with this strategy, and I was like, they're going to lose. This would be great.
How'd you know?
What?
How'd you know?
Well, so you actually, I believe you partitioned the work equally, right? Everybody ended up doing a quarter of the work. So everything was partitioned equally. It just turned out like the cost of kind of getting it all partitioned equally and synchronizing it all back up ended up overriding the cost of work imbalance of you computing a few extra numbers. And that's something that's going to happen in this class. And this is it turned out to be a fairly unpredicted but good example of designing a more complex algorithm that sort of feels like the right thing to do, but in the end of the day, constants kind of do matter. So thank you guys very much. That was very good. Okay. So takeaways from demo 2 should be that, first of all, everybody identified properly that we had this situation of work imbalance. Work imbalance limited their ability to get this perfect 4x speed up. And that by improving the distribution of work, they improve speed up, which usually happens in this class. In this demo, that actually didn't happen because the overhead, again, of communicating swamped the benefits of the better distribution. So I think that was a very nice demo for everybody. Okay, so let's go to one last demo before we get on to some other things today. So here's what I want to know. I want to know the total age of everyone in the classroom. I want to add a rough estimate. So what are some ways that we might be able to do that? Let's start thinking about an algorithm. I want to add up the age of everyone in the class. Yeah.
Maybe like people in the back start and then tell the people in front of them, and then when they get to the front, they go to the middle.
Okay. Okay. Yeah. Add a cheap row. Okay. How about I could walk to every one of you and I could ask you your age and I could add them up? It's a reasonable idea. Yes?
Each person can add their ages, and then 4 people can add the 2 numbers, and then 8 people, which will grow.
Yep, so you could do the binary combining tree that I imagine you guys might have learned about in 210. Yes?
Yeah, we could count each group of people with the same ages.
Yep, we could enumerate ages between like 15 and 25, and then count how many people raise their hands, and then we can do the multiplication. Good, okay. So which one do you guys want to try? Yeah. So, depends what you guys want to get out of this class. Okay. But hold on. So somebody make a passionate case for one of the algorithms. All of them seem like reasonable, plausible strategies, except for the one where I go around and walk around. See the rows? What about the binary combining tree one? That sounded cool too. So rows? Yes, sir?
Like, I think the like hash table approach with the like partition by age is probably gonna be the fastest, but then because of overhead people getting up.
Okay. What if I tell you this? You can't shout. You only can talk to your neighbor. Because you just, yeah, that's your neighbor. Yeah. So shouting is a pretty different network, right? And quite an expensive one to build. So how about I tell you, just let me add another constraint. So you can only talk to your neighbors. Okay, so it's rows. Seems like a reasonably simple enough we might be able to succeed. Okay, I'll start my watch.
Oh my god. Wait. Can we figure out a process to this first? Shit.
You ready?
Okay, alright. Going that way. We're going that way.
We're going that way? And then we're going up? Okay, so I'm hearing that you're going to go that way and then you're going to go this way. Those are the only details of the algorithm I know.
Yeah.
All right,
So after
everybody ready?
you should get a number, right? And then that person will get a number.
Okay, time out. Time out. Ready? I'm going to give you a total of 2 minutes. See if you can get it done. Ready? Go. Go.
20. Tell me what your number is now. But you also need, oh, okay, well, there's another 119. We're adding another 119. This is not well planned.
Oh. Come at it this way. Where's the current state of the reduction? Okay, I suppose I'm supposed to get the answer from you. Okay. It's almost there. Number? 1,571.
150 people at this point, you're saying?
Yeah. The average age of the classroom is 10. Okay. So what point do you think I'm trying to get across in this demo?
That we suck at math.
No, I'm not trying to get across that you're not so good at math. I mean, everybody in here is perfectly good at math. Probably better than me. Yes? Not as complicated. The thing that I'd like you to take away from this demo is that for a lot, because you would think that adding up 150 numbers is a very parallel computation, right? It's a pretty simple computation. Like you could write that code in a for loop pretty easily. But in this particular case, the problem that I gave you has an enormous amount of communication, talking to your neighbors, compared to the amount of computation in it. I suspect most of you were spending most of your time talking left and right versus actually doing arithmetic. So it really didn't matter how good at math you were. You could have probably done the math with an abacus. And if it's just the pattern of how you're communicating is the most important detail in this example. And so communication costs can absolutely limit our speed up, especially when we get to large numbers of people or processors. And that is going to be, even though this is a parallel programming course, most of what we do, or most of the challenges that we face in this class, is trying to orchestrate all of these different processors in the machine. Okay, so let's get on to some new topics then. So the number one theme in this course that I want you to start thinking about is that you will be thinking about is designing and writing parallel programs that scale. And by scale, I mean effectively use large numbers of processors. So that's going to be decomposing work into pieces like I did here for the students, where I broke it up into 4 pieces, assigning that work to different workers, or maybe redistributing it if it was unequally imbalanced, and then doing all the necessary communication to keep everything in sync. And so we're going to talk about techniques for writing these kinds of programs, but we're also going to talk a whole lot about abstractions and the way to think about writing programs, and programming models, and things like that. So we're going to talk about algorithm design and coding. We're going to talk about abstractions and semantics of programming languages. And we're going to talk about the actual underlying hardware as well. Because if you're writing a parallel program, you're writing that program because you want to go faster. And there's not an asymptotic number of processors in the system. Most of the time, there's a very fixed number of processors in the system. And that's a constant. So if you don't care about the constants, or you care about the constants because you're parallel programming, so you better know about some of the machine constants and the properties of the machine. Like, for example, one computer that we had up here in the early demo had a really, really slow communication network, right? And another computer had a really fast communication network that would have brought the students together. The right way to design the algorithm depends very much on the properties of the machine, which is why we have to tell you a little bit about how machines work. So we'll talk about hardware as well in this class. The last theme in this class is efficiency. So a lot of people like to think about faster. And really in computing these days, we care a lot more about efficient. So for example, is it good or bad? Would you say it's good if I had 10 people up here, and 10 people were able to give me a 3x speed up? Is that good or bad? What do you think? So I heard it bad. Who said bad? Bad. You said 3x speed up with 10 processors or 10 students is a bad idea. Why might that be why might that not be successful? So in other ways, let's say that you were working at, you don't want to say like an employee should take this spot? No, that's right, I can't remember. let's say you got that job and you went to work and somebody told you, here's a 10-core processor, and you came to work the next day, here's an algorithm that's a 3x speed up. Are you fired or are you given a raise? Who thinks you should be fired? Isha thinks you should be fired. 2 people think you should be fired. Why fired? Yeah, go for it.
Because it uses a lot of resources.
Used a ton of resources and didn't get linearly proportional benefit for those resources. Who thinks you should be given a raise?
Well, like what if you're like a high frequency trader and you made like millions of dollars for a company?
That 2x or that 3x speed up might be really, really valuable, right? So the metric of what is good very much is going to depend on the problem. And so understanding the problem, like here, let me give you another example. Imagine you're a game developer making the next Call of Duty, and your optimization allows you to go from 10 frames per second to 30 frames per second. You get fired or you get a raise. You probably get a raise for that one, right? So sometimes our goals of performance are very different based on the application. Okay. Yeah. So from the programmer's perspective, if I give you a computer, most of the time, you as a programmer, as a software writer, would be like, yeah, I want to be efficient. And by being efficient, I want to make good use of the machine's capabilities. If I give you a 10-core processor, yeah, sure, I'll strive for 10x speed up. So that's the perspective if you're in software. For those of you that are ECE in this class, you might be designing hardware itself. And so for you, your perspective of efficient might be, what are the capabilities I should put in this chip so that everything I put in the chip is used effectively? Like if I put in a really, really slow communication network, maybe I shouldn't put in all these cores because they're never going to be able to talk to each other. And things like that. So those of you that are here thinking about designing hardware, efficiency is what combination of hardware resources should I make for a problem? For software architect, efficiency is, given what the hardware architects have given me, how can I make best use of it? Okay, so any questions? Any questions at this point? No questions? Okay. Cool. So let me take a little bit of an aside here. Let's go through a few logistics for the course, because a lot of people here are probably sitting in on the course, or sorry, sitting in, and you may even be on a wait list at this time. So let's talk about a few of the boring logistics. What we're looking for everybody to do to get started is that we have a course website. We have Piazza. We use Piazza for all the normal Piazza stuff. We have a course website. I would like you to sign up for an account on the course website. So our course website has a login. Please sign up. And the reason, so we have no textbook for this course. And so the only material, the reference material of the course is our website. All the lectures are filmed, so we don't have a book, so you can go back and watch the lectures. The website has all of our slides. And the website has the ability underneath all the slides for you to ask questions. And those questions can be answered by me, they can be answered by Professor Bryant, maybe the TAs, or maybe one of the other students in the class. So last year, the students in this class, and there were far fewer students in the class last year, generated something like 5,000 comments on the website. And as you play around the website, you can see like if somebody responds to your comment, you'll get an email saying so-and-so answered your question and stuff like that. So that's why you need to log into the website.
Question?
Yes?
Do the responses to the comments that you make on the website come about as fast as if the same question had been asked on Piazza?
Good question. So we will not use the Piazza for anything of any intellectual merit.
What?
You use Piazza to ask me when office hours are. You use Piazza to ask a question about like, oh, this is breaking, this code's breaking, or I have a particular question about a homework assignment that needs to be private. If you have any question about course material, I would prefer that you ask it on the course website because it benefits people a lot more. They'll see the question, they'll see the response, and when you're going back studying for the exam, any question you ask on Piazza is gone 3 weeks later, right? You'll never find it again. Here it's right underneath the slide where it was pertaining to.
And this pertains to homeworks as well?
Well, you should not ask a question that obviously is like, is this the right answer to homework 3?
Yeah, right.
This is more like a bunch of students are really studying, and they want to know, and they're working through some of the course material. So let me pop it open. I forgot to pop open the website. But
Good man.
show it to you real quick. So here's our course website. And if you look, like the first lecture is always up. And notice that like you can go underneath one of the slides, and I've actually asked a question here. So you'll see myself and my TAs populate the site with a bunch of questions. Like for example here, in 213, you ended up spawning a bunch of p-threads, right? You wrote a program that created a bunch of threads. So why did you create those threads in 213? Yeah.
It was mainly to deal with like latency on like UI.
So you're never really thinking about a parallel program in 213. I mean, maybe these days they certainly talked about it, but in 213, you created a bunch of p-threads in your proxy. Right? It's still a proxy.
Yes.
Okay. You created a bunch of p-threads in your proxy, and so the idea was you had this really long wait time to go out onto the internet and wait for a response, right? So why? Let's refine this notion a little bit. Let's answer the question. Why did you create a bunch of p-threads? So it has something to do with latency.
Responsiveness.
Right?
Responsiveness.
And what do you mean by responsiveness?
You have multiple users who are not all waiting on some other person.
Right, so you like say, oh, if my proxy is busy servicing, downloading a movie from Amazon, I don't want the next user to have to wait for 2 hours if they're simply just trying to grab index.html from cmu.edu. So you wanted this concurrency for sort of quality of service. You wanted the concurrency to hide latency, which was while the proxy was waiting on the request from CNN.com, it could be servicing some other request. Why might you spawn a bunch of p-threads in this class?
To run them in parallel.
So we can run them in parallel on different cores. So if I said that, what would you say is different between this notion of concurrency, which you dealt with in 213, or you probably dealt with in operating systems as well, for those of you taking, and parallelism? Yeah?
Concurrency is about making abstraction easier for us to use, while parallelism is about making it so we can actually do more at the same time.
So this is one of the first good examples of this class of the difference between an abstraction and an implementation, right? Concurrent processes, or concurrent work, is work that may be running in parallel. You have to make the assumption that it's running simultaneously, but there's no reason why I couldn't implement the proxy by handling one of those requests to its completion, and then the next, and so on and so on. So regardless whether or not your proxy was running on a parallel machine or not, it was a good idea to implement your program in terms of these concurrency primitives, and to interleave them perhaps on one process. Here we're going to actually create those independent things to do so we can run them in parallel. Exactly. So this is an example of like a question I might post on the site. And for example, last year this ended up in like a 20-comment discussion about, okay, wait a minute, what was he really meaning by the difference between parallel and concurrency, and so on. So that's what you would might do on the site. The other thing you can do on the site is if you really, really don't want anybody to see what you're saying, like if you're studying for the exam, you can put notes to yourself, and trust me, like unless I run a SQL query, nobody will ever see that. So the site has sort of some things for you to do with that. And then of course there's a feed up here which says everything that's going on in the class. So you can see that I've sort of primed the site with a number of questions which all of you can go try and answer. And by try and answer, I mean you should answer. Because one of the requirements of this course is that we ask you, in order to think about every lectures more often than just when the midterm comes around, you're required to post one reasonably well thought out comment on the website per lecture. So we're not crazy about this. If you decide to miss a lecture, you can do 2 on the next lecture. But no, you cannot come back at the end of the year and post 27 comments on the last day and expect to get that participation required. So the point of this is, as you're thinking about the class, just go ahead and write it down, because writing it down is going to benefit everybody else or benefit yourself. A lot of students say, I can't think of anything to say, and here are a bunch of things that might be useful ways to add a comment to the website, such as just explain the slide. If you want to explain it in the lecture, go watch the lecture and try and explain it in your own words for everybody else, because maybe you could do a better job than I can. If you're completely confused, tell everybody you're completely confused, and somebody will unconfuse you. There's 149 other people to unconfuse you. Or you can do things like ask your own questions, go say, hey, Caitlin talked about this in class, but I find this guy at maybe UC Berkeley did a much better job explaining it. Here, why don't you just go watch this guy's lecture instead? It's better. That could be a useful contribution, and so on and so on. Especially in this class, mentioning real-world examples is a good way to participate. We're going to have quizzes every 2 weeks. This is something requested by previous year students about not having a textbook. They wanted more review material. So every 2 weeks, we are going to distribute a quiz. Most of the time, those quizzes are like previous year's exam questions and stuff like that, so just kind of practice as you're thinking about the problem. They'll be distributed Wednesday night. They're due first thing in the morning on Friday. And they're take home. We want you to do it yourself, like an exam-like situation. But that's just to force you to think about the material. We will grade the quizzes, hand you back a fully marked up thing, and we're going to put in the grade book a 1 or a 0. We put a 0 if you didn't try at all, we put a 1 if you made a solid effort. So they're no stress, low stress quizzes, but they're meant to get you to have some problems to think about as the course goes on. We will have 4 programming assignments in the class. The 4 programming assignments are here. We change them up a little bit every year. This year, almost certainly assignment 3 will be brand new. And they're all on different computers to give you a different flavor of different types of parallelism. The first assignment you need to do on your own. The rest of the assignments you may do optionally with a partner. It is not required. Many students can go through the whole class without a partner, but sometimes it reduces stress to have a partner on these things. So we'll have 4 programming assignments. And then, as you'll notice, like the 4 programming assignments are boom, 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 boom throughout the first half of the semester. And the last part of the semester, the last 6 to 7 weeks, is your big final project. So this is something that you probably want to start thinking a little bit about now, because some folks really have fun with the final projects. So the final projects, as you may have heard about, are presented on the last day of our final exam slot. We don't have a final, we have an in-class exam 2. And for the top projects in the class, where top is designated by our guest judges, we go invite a bunch of friends from industry, come in and have you present your projects to them, and the winners, just for fun, get prizes. So what are the prizes? Who knows? But the first prize that's already been given to give out to you guys this year is this Apple Watch Sport. So it's prizes on this kind of level of stuff. So this is one of our things that we're going to give away at the parallelism competition at the end of the year. A couple years ago, Apple showed up with like 6 iPads. And nobody wanted them, actually. because Citadel showed up with a couple of drones. And everybody wanted the drones. So this is just something you should start thinking about. It's the last, you can think about this last 7 weeks of the project, the 7 weeks of the course as a big independent study. If you're interested, last year's projects are right on this link here. And that's basically how it works. The grade breakdown is, notice that we push you hard in this class. We're going to do a lot of stuff. But I think most people feel like the grading is relatively easy. If you notice, both those exams total up to just 28% of grading here. So we'll give everybody a bunch of different ways to do something that they like in this class. If you like coding, you're going to keep yourself busy on the programming assignments for sure. If you like thinking about conceptual things and the programming laws and abstractions, you have the exams and the quizzes and this participation requirement, and all of you have the ability to shine in the final project. Okay, so that's our logistics. Are there any questions? Just please make sure you sign up on the website.
Is there like a code for the website?
Oh, there is. It's on Piazza, yeah. Just to prevent anybody in the world from signing up, I have a secret code, and the secret code's on Piazza. I think it's too many cores or something like that. Yeah. Any other questions about logistics before we get back to some fun stuff? No questions? Awesome. All right. So let's get back to a little bit more about why we're here. So if you were in this class 15 years ago, and Professor Mallory did start this class 15 years ago. In fact, I took it when I was an undergrad at CMU, and there were like 9 of us in the class. There really were about 9 of us in the class. And 15 years ago, which I didn't take this class 15 years ago, just for the record, is that if you wanted to write parallel code, you were doing so probably because you wanted to run on a really big computer running at a national lab or a big corporation like IBM. And the reason why most people were like, this parallelism thing, who cares, is that processors were just getting faster every week. And so that's what this chart is plotting, is that for the longest time, so the x-axis is time, the y-axis is the performance of the CPU, how fast it can run one thread of code. And you see, and this is a log scale, and you can just see it going up. It's going up exponentially. So every, I think it's not quite Moore's law, but like roughly Moore's law, if you just waited 18 months, your code was twice as fast. Because the process is really better. And as you can see, like this parallel programming thing is not necessarily the easiest thing in the world. And so most of the time, people are like, I'll just wait a couple, I'll just wait till the next Intel 486 comes out, the Pentium 4 comes out, and my code will just be faster, so let's just not worry about it. But now we have 150 people in this class. And CMU is not 15 times bigger than what it was then. So that's sort of why I asked at the beginning of the class, well, why is everybody here? All of a sudden there's a lot more interest. And why is that? Why don't we just, let's just go take something else. And we'll just wait to 2018 and computers are just going to be faster, so why are we bothering with this at all?
The latest Core i7 is not that much faster than the first i7 that came out.
Okay. On what? What do you mean by faster?
By a single core performance.
A single core performance. And what do you mean by single core performance?
It's, frequency.
Okay. What do you mean by frequency?
So
So what I mean by this, so this is actually really interesting, is I found that when students are forced to write a comment, everybody will read it and go, wait a minute, what do you mean by that? And then it actually forces you to think a little deeper, and so on and so on. That's why we write in this class. So everything you said is exactly correct. You said that today's, if you go buy a processor from Intel today, 2016, and you compare its single-threaded performance, if you compare performance of a program that only has one thread in it, to basically what Intel was shipping, I don't know when the first Core i7 came out, but 5 years ago, it's not going to be that much better. It's not going to be that much better. Well, let's talk a little bit about some of the reasons why. So up until about 10 years ago, there were kind of two major ideas. Like if you took an architecture class, there were two major ideas that you can attribute a lot of the speed-ups from processors to. The first thing was increasing clock frequency. What do I mean by increasing clock frequency?
Processors could do more and more instructions per second.
So that's increasing the rate at which instructions are executed. So instructions per second, good. And exploiting instruction level parallelism. So I'm going to talk about both of these things. I'm going to do them two first and then one. So let's talk about number two first, because that may be a term that a lot of you may not have heard. And so what we're going to do here is we're going to start in this 4-level class by a little review. And I want to ask the question, what is a program? What is a program? Let's go back to 213. What is a program? What is a program from the hardware perspective? How about that? It's a sequence of bytes in memory, and we can assign a little bit of a semantic to those bytes. So a program is just a sequence of instructions. It's a to-do list. Right? So if this is a program, and this is, in fact, part of the code from assignment 1, I compiled it, generated this. What does a processor do? So we know what a program is. It's a sequence of instructions. What does a processor do?
Fetch, decode, execute.
Okay, and that's a lot of terminology, but let's just see, what do you mean by that?
It has like the program counter, so it points to an instruction, it grabs the instruction from memory, figures out what that instruction is, and then it does that instruction, puts the remaining stuff like back into memory elsewhere, registers or whatever, and then it grabs the next instruction.
That sounds good. So if this is a sequence of instructions, what does a processor do? A processor executes the sequence of instructions, And it does so, like you actually dove into some of the details of how it executes that sequence. But for now, I think it's a perfectly reasonable way if I wanted to think about a processor saying, hey look, we have an instruction. We are going to execute the instruction that's currently referenced by the program counter. We're going to update some state. For example, I update the value of registers or memory or processor state. And then we'll move to the next instruction. And so on, and so on, and so on. So a processor is just executing this list of instructions. So one way, well, okay, so hold on. So one way to run this sequence of instructions faster would be to just increase the rate at which I can execute these instructions. Instead of a processor going boom, 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 it can go boom, 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 boom. That would be like learning to count faster. Okay, this is a class about parallelism. What might another way be to execute the sequence of instructions more quickly? Okay, so it's pipelining, which is not something I'm going to talk about today. But yeah, so that's a good ECE answer. Yeah. Oliver?
You have like a bunch of like add instructions and stuff like that that aren't actually dependent on each other necessarily. So you can potentially break those up and like in your encoder send out multiple instructions to different add units.
Okay, good. So that's an interesting idea. So what Oliver is saying is that even though any valid processor has to execute this instruction, then execute this instruction, and so on and so on, if certain instructions are not dependent on each other, the processor can just figure, oh look, these things don't matter. In fact, these don't matter. These are actually independent instructions. So hey, let's execute them at the same time without actually ever telling software that. So that's what I mean by superscalar execution, or instruction level parallelism is the term I have on this slide. So whenever we have instructions that are independent, and these two instructions update different registers, which means I can execute this one before this one, or this one before this one, or both of them at the same time. The processor has the ability to execute these in whatever order it chooses, so that things can be a little faster. In this case, this multiply uses as input R1, which was generated in the previous instruction. I have to do this first, and then this. So processors have always been relatively parallel. Just Intel didn't tell you about it. You gave it a sequence of instructions and said, do this, and do this, and do this, and do this. But Intel was building smarts into its processors to say, hey, look, I can actually do both of these at the same time, and the user would never ever know. Because the values will end up being the same. So how would you, if let's say you were working at Intel, and I gave you this expression, I'm now writing it as an expression, what parallelism is there in this expression? So there's three. What are the things you might potentially, if you didn't want to tell me about, if I didn't want to think about parallelism, I just said evaluate this. What might you do?
I would calculate x squared, y squared, and z squared separately.
You could okay.
Or like use two other people along with myself to calculate them.
Exactly.
X, Y, and Z are, say, 8 bits, and I have a 32.
Oh man, okay. So you're going to pack 8-bit values into a word. That's another form of parallelism. I guess I haven't even talked at all about the bit level parallelism in an adder as well, but that one might be a little bit more of this class. So if I actually just draw the dependencies between the operations to evaluate this expression, notice that I say here, the amount of parallelism is 3. Here there's 1, and here there's 1. So why is there only the ability to execute one thing at a time down here at the bottom of the graph, but there's the ability to execute 3 things at a time at the top of the graph?
Independent.
Yeah.
Because the multiplications are independent of each other, or they each depend on independent.
Absolutely. So these 3 multiplications are independent of each other, but these additions depend on previous results. So the semantics of the program the dependencies of the program fundamentally require some serialization. So they were studying this phenomenon quite a bit back in, it was probably hardware architecture of the mid-90s. They said, well, in general, if I just look at normal programs, how much parallelism is there? 'Cause who knows, maybe there's a lot. And some students produced this graph. So the x-axis of this graph is what I'm calling instruction issue capability. So that's how many instructions could the processor do at once if they all happen in parallel. So for example, here on this slide, if I had a processor that could execute 3 instructions at once, that processor could do a great job up here, and then not so good here, and not so good here. Or in other words, I could only utilize the ability to execute 3 instructions at once at the beginning of this program, and then I would have to serialize the program and not use all of my resources later on. So that's what this graph is showing on average over a bunch of different programs. If you increase the ability for a processor to execute instructions at the same time, without telling the programmer at all, it still sees the same list of instructions, how much performance benefit do you get? So if you were working for Intel, or these days ARM, what type of processor would you build? Because it's going to cost you some money to put extra stuff in the processor to be able to execute, let's say, 16 instructions at once, if the program allows you to do so. What processor would you build? Now I want you to think like an architect. Yes?
I have 4 ALU.
You want to be able to do 4 instructions at once. So why did you pick the number 4?
Because the graph shows that we get improvements until 4, and after that, the improvement is not as substantial.
So you're saying as an architect, you could make this chip that could do a lot more, but much fancier. It would look really good in marketing material. But it wouldn't in practice be very useful, because if we looked at instruction sequences, on average, it's very hard to find more than 4 instructions that are independent at once. And that's exactly what this graph is starting to show. Exactly. So, question? Yes.
Isn't that probably because the compilers don't assume you have high instructions per call, and therefore they'll generate code that will use that?
There is going to be, in every aspect of this course, interplay between what the compiler is revealing to the hardware and what the hardware can do. So in this case, what you're saying is that, what I'm saying actually, what you're asking about, is that if I look in general at programs that were not written to be parallel by you, and were not created by some fancy optimizing, auto-parallelizing compiler, in general, this is the amount of parallelism that exists. But what I'm not saying is that we couldn't create programs with much more parallelism. In fact, if that was true, we wouldn't have any parallel processors today, and we'd all be taking algorithms too right now, because that would be the only thing that mattered. Right, exactly. But this is, given the programs that were written at the time, were entirely sequential. Because there were people writing sequential programs because A, it was much easier, and B, if we just sat around and waited, adding more instruction issue capability as well as adding frequency was just going to make our code faster. Yes?
So is this more a comment on like sequential code that you write in general can be parallelized past like the 4 branch, or is it saying the compilers we have can't make it any better?
That's a good question. Let me put it this way. There's a lot of stuff in this class where my answer to the question is, nobody's been able to do it. So theoretically, you could consider, let's make a compiler that takes a look and analyzes a program for parallelism, and finds the available parallelism, and then exposes it, reorders the code so that it's friendly to a modern processor. And certainly in like a purely functional language, that makes a lot of sense. We have the information available to us to potentially do that with the compiler. In something that's a little bit more of an imperative language, where I have pointers and other things, it's very, very difficult to do that, especially statically. And so that's why you see a shift these days in the whole back half of this class is going to be about new languages and frameworks that make it easier for software, whether or not it be the programmer or the compiler, to know more about programs so it can help you with the parallelization task. Okay, so that is this notion of ILP. Is that if we do nothing to help the processor out, the processor's looking, trying to figure things out for you under the hood. And there's some diminishing returns on that. So as Moore's law increased, as they could put more and more transistors on the chip, they were using those transistors to add more and more execution capability, and more smarts to look over larger and larger windows of instructions to figure out where the parallel stuff is. Okay. So here's an interesting graph. So this is a graph, I believe Kumle made it at Stanford. Yeah, actually it is Kumle made it at Stanford. And unfortunately it's a bit dated. So a great comment would be somebody going to the microprocessor database and extending this graph out to 2016. That would be awesome. And so this plots 4 different trends in computing. And the trend that we just talked about is the purple line down here, which is what is the instruction issue capability of processors. And notice that it kind of flatlined here, beginning roughly in the year 2000, which was once processors already got to about that 4x capability, and there was nothing more that that strategy could do. Another interesting line is this green line. This green line is the number of transistors per chip. So this is basically what we're talking about when we say Moore's law. We've been able to continue to put more and more transistors on a chip, and we'll come back to that in a second. And then the interesting line is this blue line, this dark blue line, is the clock frequency of those processors. And there's something that should be very, very interesting that you notice in this graph. What is something that you notice very, very interesting? So I've already explained to you why this line taps out. But why does the navy blue line here? Well, what's going on? First of all, what do you notice? Yeah. What do you notice?
What we're doing with the ILP and how are those seem to get a pretty similarly until they reach horizontal asymptote.
It reaches horizontal asymptote, good.
And while frequency, it's linear from 1970 to around 2000 when suddenly
Basically, about when I graduated undergrad, all hell broke loose. So hopefully this is one of those things that's just correlation and not causation. But so notice here that the frequency, the clock frequency of the processor, measured in megahertz or gigahertz these days, stopped increasing and has basically been pretty darn flat for the last 10 years. Like, at this time, I could go buy a 2 or 3 gigahertz Pentium. And today, I cannot find a Core i7 that's clocked at 6 gigahertz. So the rate at which I can execute these instructions is still the same. So like the 2 major ways, if you gave me a sequence of instructions that I can use to run it faster, now all of a sudden, those just trends, they just stopped. So we talked a little bit about why this one stopped. Does anybody know why the other trend stopped? Yes, sir.
So for the CPU, it's made of tons of little transistors, and they all have like a bit of capacitance to them.
Yeah.
So in order to increase the clock frequency, you need to get the capacitance of the transistors to react a little bit faster, and the only way to do that is to increase the voltage.
Increase the voltage.
And when you increase the voltage, it uses more power, and more power means more heat, and now your CPU is melting the silicon.
Right, absolutely. So if I wanted to, so first of all, notice the size of the processor, and notice the size of the heatsink these days. And in general, in life, when things are bigger, they're very important. That's not really true, but often in computers it is. And so the power consumed by a transistor, as you were just saying, is proportional to the frequency, but it's actually more than just proportional to the frequency. As if you want to increase frequency, you have to increase the voltage. And so if I want a high frequency chip, I'm running at high voltage and I'm clocking it high. So you get this non-linear increase in power as we want to continue to scale frequency. And so just to give you a sense of like sort of where we are these days, my microwave oven in my house is 700 watts. TDP, which is not even max power, but on average power of a bunch of different processors. So in my laptop right here, if I'm using this pretty well, I'm at 45 watts. If I'm on my desktop, I'm at about 100 watts. If I'm on a fancy GPU, I'm at 250 watts. And if I'm on a phone, I'm half a watt most of the time. 2 watts if I'm really using it. So as you can see, that there's a huge concern about power these days. Whether or not you're in mobile, where you don't want to burn a battery, or whether you're mobile or anywhere, you're really concerned about heat. So having all these transistors switching on and off at a very, very high rate burns a lot of power. And in fact, there's actually a link to this on the web. There's a guy that got out an ammeter and started measuring his latest core, not latest these days, but Core i7, and empirically, here's his experiment as he overclocked his chip. I think he basically just blew it up in the end. As he overclocked the chip, here are 2 different Core i7 models and the power that's consumed by them as he's overclocking. And you can see there's a huge nonlinear increase in power consumption. I don't really know what he means at this level. So the implication of all of this now is there's no more free lunch. The 2 ways where we can just sit back and take algorithms, and then our asymptotically best algorithms would run faster the next year, and next year as processors got better. So as we got the constant benefit from better and better processors, that benefit has largely gone away. So the answer 15 years ago was, hey, I want to run supercomputing scales. I wanted to go run at the Pittsburgh Supercomputing Center. I want the hugest possible computer so I can do something that's not possible on a desktop. Today is that it's basically the primary way to make your code run faster once you've completed your algorithmic improvements to the code. You cannot sit back and wait for Intel to deliver you more performance tomorrow and the next day. And I put a little asterisk on this, using the term primary way, because I'll add another dimension to this problem about 2 months from now. But for now, for the first half of the course, parallelism is the way you get performance. And you're not going to find a chip these days that's not highly parallel to some extent. So here is Intel's Skylake architecture, which is you go off on the Dell website and buy the latest and greatest Core i7 that was shipping in 2015. It is a quad-core CPU with a GPU in it as well. And so you can almost read it off from the chip where the various components are. So you really can't buy a single-core processor anymore unless you're working at the lowest end of ARM or something like that. An interesting thing to note is that those 4 CPU cores now are dwarfed on the die by the GPU. And we'll talk a little bit about that later. That's a pretty interesting statistic because you can tell what's important at Intel by how much die area they get. And now that the die is dominated by the graphics chip, it's kind of interesting. Here's another example. It's a 61-core x86 part called Xenon 5. And you can still just like read the cores off from the die photo. And in fact, we have 15 of those for you to play around with in our lab, in our cluster. And so you'll do assignments on these guys. So these are 61 cores, all on one chip. They're basically like 61 little Pentium 4s. That's what they are, with a really big vector unit. We're going to talk a little bit about GPUs, which is another style of processor that was invented and started for graphics, but now you should just think of as another form of parallel processor. And so this guy has 16 major building blocks on it, if you count them out. And this is not just high performance, this is about efficiency, remember. And many of you will end up doing most of your programming on mobile going forward. And if you look at all the mobile parts, we have NVIDIA Tegra K1, quad-core ARM plus GPU, very much like a mini version of that CPU, the Intel CPU I just showed you. Apple's A9, dual-core CPU plus a GPU plus a special processor in there for image processing. Everything is parallel. And then we still have the high end. So the United States' biggest supercomputer, and the world's number 2 right now is in a lab called Oak Ridge National Laboratory, not Los Alamos. And it has about 20,000 16-core CPUs. Let me check. Yeah, 18,000 16-core CPUs, which is a total of about 300,000 cores. Plus, every one of those nodes has 18,000 GPUs in it, and that's like another 500,000 or 600,000 cores. So if you write a program for this machine, you're basically writing a program for about 1 million cores. It's a large machine. It also has a power budget of like $2 million a year. Okay, so I'll stop a little bit early today, but that's what we're going to be talking about. The main idea is that single-threaded performance is hard to get faster from single-threaded performance, which means the easiest way for architects to give you faster and faster chips is to give you chips with a bunch of different processors in it, which means you're going to have to write parallel code. And that's what we're going to talk about largely in this class, or at least the first couple months. And yeah, welcome to 418. Thank you very much.